Okay. A very good afternoon. I have posted these notes on the on the Moodle. I hope you're able to access this. Um, Sorry, my throat is just not recovering. um, I don't know if you saw the moving tough. I don't know if you saw this latest announcement from Prasad Bhai Karandikar about Bharat Jan. That is what is keeping me really, really busy. My throat is simply not recovering. So do look at this post from the minister as well. And um, of course, featuring the Prime Minister's talk. Maybe later today I'll show this. So that's one of the reasons my throat is simply not recovering. A good reason, but it's unfortunate for you guys. I hope you can hear me. There's too much travel. I mean, to make something national, you need to move heaven and earth, basically. Okay, so I hope you're able to access these slides which I had shared. These are basically the notion of different notions of convergence. I will maybe visit them once, but this is really optional. I had left you last class with a homework, food for thought. What's the relationship between the rate of convergence we saw and the theta and the omega and the O, right? So the answer is this is a different notion altogether. Well, there is certainly a bound. We'll see that again. It's a bound, but it is not like the tight bound or lower bound. I mean, tight upper bound or tight lower bound. So we'll talk about this. But yes, the homework still remains. And our notion of convergence, is it more related to theta or omega or Vigo? Where do you see the connection? Anyone give a thought? Okay. Okay, so we'll continue this. We saw how by invoking Lipschitz continuity along with convexity gives you a very, very unsatisfactory rate of convergence, right? So how did we go about it? Let's just write down our building blocks. What were our building blocks? How did we come to this point? I would like you to suggest, right? How did we come to this point? How did we get E1, which is a sum of differences of subsequent of iterate function values that iterates from the function at x star. How did we get here? And this you saw, this was independent of the gamma, the step size. So what were the elements? One was algebraic. And it's good to write this down because these will keep recurring. So algebraic, which is a dot product GT transpose f of, sorry, x star, something like this, right? Clearly different, something of this sort. And in terms of the right? It was like a x1, x2, roughly x1 transpose x2, right? Instead of getting into the specifics, it was x1 transpose x2. We wrote it as x1 norm square plus x2 norm square minus, okay, this is 2 times, minus it's a simple algebraic trick. What is the other trick? Huh. Yeah, so telescopic summing. Yeah, telescopic summing. Right, so which led to, you had, let's say, f of x t plus f of x t plus 1 plus f of x t plus 2 up to x t plus 1 minus f of x t 2 and so on, leading to cancellations of these intermediate terms. What was the third property? Of course, we made use of Lipschitz continuity, right? And convexity. Then we also used some bound on the initial iterate. What was it? X naught minus x star. The distance is less than or equal to r. Basically, the further away you're from your optimal point, the more time you will take. Anything else? Okay. So with all of this, I think, oh, by the way, we use one more trick I forgot. The fifth trick was right here. If you have an LHS, which is independent of gamma, less than or equal to RHS, which is a function of gamma, what could you do? You could minimize the RHS with respect to gamma and still have the equality. Now, this is not the most ideal thing to do everywhere because you want the gamma, a specific value of gamma to be used. But nevertheless, it's not a bad idea, right? At least in the convergence analysis. It may not be the gamma you select, but obviously you may say, well, there has to be some coherence between the gamma you get here, the gamma that gets used. So those are valid concerns. But this is okay. I mean, this is just saying that this holds for always. Well, it should also hold for the gamma which minimizes. That's it. But before you go overboard on it, you may want to be a little careful. But this is fine. So we used all of this. So we got this expression E1 independent of gamma. That's what you see here. Right hand side which is dependent on gamma E1 E2. And then you minimize the right hand side with respect to gamma. That's the last. This was the last step, right? Set the derivative of the right hand side with respect to 0. I called it trick 3, but that was, I mean, on the board it is trick 5. The order can change. In fact, for different convergence analysis, the order does change. So at times you use, like, I'll give you a hint, like when we start looking at strong convexity, but convexity came in a bit late here. Strong convexity, you might want to use it upfront, right? Especially terms that involve quadratic expressions, may want to bring up earlier rather than very late. Telescopic summing should be after things are simplified a bit. I mean, just apply your common sense. Which one may be invoked where? Okay. Okay, so we did this, and then there was one more trick basically, which I talked about, but no, I didn't write on the board. So after we do this, you do you do a telescopic summing. Now the thing is, when you have an expression like this, summation fxt minus fx star less than equal to rb square root t. Now this expression fxt minus fx star summed across all values of t could be approximated with respect to, if the summation is less than equal to rbt, then what is guaranteed? What is guaranteed? If I take the minimum of this t times, minimum of the left hand side t times, right? That will also still be less than equal to the RHS, right? So that's the sixth thing. That's what you are bringing up here. Summation of LHS, but this is a function of t. T equals 1 to t less than equal to RHS, which is independent of t, implies min with respect to t of LHS t is also less than equal to RHS, right? So that's what we've done here. Choose if the summation is there. Sorry. There's a small t times. Okay, t times the min. T times the min, and that's what we did here. 1 upon t was there, so we multiplied by t. They cancel out. So if we choose x hat to be the iterate that minimized the f, right? Then the inequality will still hold when you scale it by t. So you can see this on this plot. That's what we're trying to show. The function is decreasing. By the way, we haven't assumed anywhere that the function does decrease at every step. We haven't shown that. And I'll give you a little heads up. Moment you use Lipschitz smoothness, the beautiful property of Lipschitz smoothness is with gradient descent and Convexity force, it gives you guaranteed decrease at every iteration. Okay, unfortunately, okay, so that's, I mean, some interesting things, okay, side points. Lipschitz continuity plus convexity don't assure guaranteed decrease at each iteration. On the other hand, I'm looking forward to smoothness implies guaranteed decrease. Okay, so I won't be writing so much on the board hereafter for the different other analysis. Will just take all our time. But these meta points will be useful for just the points of difference. And in fact, I've given you as a homework, right? Think about what Lipschitz smoothness will bring. This is one difference it will bring. We'll see some more side points coming up as we progress. Okay, so this, unfortunately, because there's no guaranteed decrease, you can't say, oh, just take the last t. You can't say that, right? So you have to say, oh, there exists some x hat which is minimizing so far, minimizer so far. So little hard work here. Okay, is this clear so far? Okay, so now when you define x hat as the minimizer, RB divided by square root t is your right hand side. So now it's just the remainder of the analysis, right? If I want to ensure that the gap is less than epsilon, what will I have to do, right? If I have to ensure that the left hand side is epsilon. Now this is where the correction with O and theta and omega will come. Okay. What do I have to do? Is there a necessary condition or sufficient condition is my question. So can you have a necessary condition here? No. Only talk about sufficient condition, right? A sufficient condition under which so if this if you want to find if f of x hat minus f x star is less than epsilon, right? Then what you could do is to try and ensure that RB required divided by square root t is less than epsilon. It's a sufficient condition, not necessary. Please note this. Okay. Actually, I'll write this at the bottom because this is common. Convergence analysis. Initially, I mean, we'll talk a little bit about history based on sufficient a sufficient condition. For example, here is RB divided by square root t is less than or equal to epsilon. This implies okay, so your RB by square root t less than or equal to epsilon implies absolute value of fx minus absolute value of x in the sense fx hat. Okay, the best it right. Okay, with smoothness things will change. So we'll keep this on the board. Okay, that will basically mean that r square b squared divided by epsilon square is less than or equal to t. T, at least you need at least, right? So what is it saying that t is greater than or equal to r square b square by epsilon square. You need at least t iterations are needed to ensure that as a sufficient condition for the difference of the function value from the optimal being less than or equal to epsilon. Is this clear? This is a sufficient condition. Okay, so and now is this related to big O, big omega, theta? Which of them? I mean, where do you find the closest connection? It's not of the same nature, but where do you find the closest connection? Huh? Big O. That's the closest connection, right? So yeah, so sufficient condition. T should be greater than or equal to r square b square by epsilon square. Okay, so that's what I left you as homework. So it is certainly more related to, and sometimes you'll find papers, etc., just using big O in a very casual sense. They use it because it's very related. Yeah, big omega is more about limiting the lower bound behavior, especially when epsilon tends to infinity. Okay, so but specifically this rate of convergence and order of convergence is what I have referred to in these notes, right? So there's something called order of convergence, linear, superlinear, sublinear. And then there's a rate of convergence, which is pretty much what we are talking about. Okay, I won't really, I mean, I'll see if there's a need, I'll go over this. But there's a notion of Q convergence, R convergence, Q linear, superlinear convergence, R superlinear convergence, and so on. Okay, so and I take the specific example of Lipschitz continuity, where you have this very, very weak thing. So what we get with Lipschitz continuity is probably the most despicable, yeah, kind of R convergence. So Q convergence is slightly better, but Okay, so I will not go over this right now. I've left it as, I hope you're able to access it. This link, sorry, this unfortunately Moodle will give me a very, very long link for this slide. I don't know why. So I've put it in very small font, but I hope you're able to access it. It's in last week's slides as well. Okay. Okay, so now we're done. And now the next, as I said, the next set of proofs will be much faster. I'll not write much on the board. Be the same set of, as I said, the tricks will be similar. 6 plus tricks will be more tricks coming up, mostly based on smoothness and strong convexity. Okay, so is this good? I think one question is how bad. I mean, we know it's bad. I've been already bad mouthing it, right? But how bad is it? Let's get an idea. Why is R square, B square, epsilon square so bad, right? I mean, advantages, of course, we have got something. It goes to 0 as t gets large, fine. And it's independent of the dimensionality of the gradient or the input space. I've written a little bit of notes here. Of course, there's an assumption being made here, right? The assumption is this one, that we are beginning within a radius r. X naught minus x star is less than equal to r. And we're assuming, so the kind of convergence is independent, or rather, it's ingrained. R is ingrained, right? Now, obviously, if we change the R, maybe the order may not change. Will the rate change? Yes, possibly, right? So, so R is characterizing the initial iterates distance only. So there is an R. That's a point to note. The disadvantage is a slow convergence, very slow convergence. To achieve an error of 0.01, we need 10,000. Basically, I mean, you need to add 2 zeros every time you add 1 decimal point. That's how bad it is, right? Also, right, here 4, I added 3 decimal points, 4 decimal points. Now it's 10 raised to 8. This is pathetic, right? Also, you may say there are other disadvantages. Does not assume that the step size gamma is obtained in a more principled search-based manner. So I said that gamma itself, the choice of gamma itself has a lot of discussion around it in literature. Of course, we'll revisit this when we talk about Anagrad and others. They also talk about it. But I have put the same set of slides also talk about at least the more conventional, well-known principles. Gamma should be chosen such that there is sufficient decrease. Is intuitive. But what is that sufficient decrease? Right? Gamma should not lead to overfitting or stepping over, right? So this slide, same set of slides. I also have that, right? So gamma can be obtained using search techniques such as exact backtracking ray search. So what is exact ray search? I mean, for simple things like this, exact ray search may be possible. So exact is the simplest. If I have gamma star at every iteration, okay, gamma t star is argument with respect to gamma of f of xt plus gamma times the gradient of minus the gradient minus gamma times gradient of fn. If I fix t, if I have an xt fixed, I know this is my direction gradient and this is my xt. So I have that fixed. I'm just trying to solve a one-dimensional optimization problem. How much should I step? So this is called exact ray search or exact line search. Sometimes you can solve it exactly, right? But the problem is many times you can't solve it exactly. And if you spend too much time trying to solve it exactly, it may not pay rich dividends because your current xt itself is a intermediate point. I mean, right? It's like preparing for the end sem based on what has been covered until today. I mean, this is just an intermediate checkpoint. You need to understand the whole gamut of the course, right? So again, in the same set of slides, I provide that exact. Okay, so exact research. What is exact research? T. Okay, I use T here instead of gamma. Tk plus 1 is R over T of f of xk plus T times delta xk. Then I use delta xk as the step size. Or step, sorry. But then there are other backtracking research. So what does backtracking research do? It says, well, um, I will do a little bit of kind of binary search. I'll do a little bit of binary search here. So so relatively simple research iterates over values of step size starting from 1, scaling it down by factors after every iteration. Okay, I'll see maybe the next class we will do a little bit of it because it'll be the last class before end. Right, but then there are other conditions which are more interesting called the RVO conditions. Say, okay, do whatever you want, but stop when a sufficient decrease condition is reached. And I think the best picturization is this one. So so while you would have typically, right, taken this step, taken this step, this is saying, okay, take a step so that there is sufficient decrease in the function value itself. Ultimately, you are not just interested in just doing a search along this direction. What you want is there is decrease in the function value. So that's the RBO condition. Simply ensures that, so this is the step. So f of x plus delta x is less than equal to fx plus some c1. So c1 is the RBO constant factor or whatever. Right? The dot product of the gradient with delta x. So when c1 is the one, right hand side gives a lower bound of the value of fx plus t delta x for a convex condition. So you say, well, that is true, but how much can you further decrease it? Okay, so I'll go back to the main slides. This is just to give you an idea that the gamma itself, all right, the gamma itself could be obtained in a more principled manner. Just going by a gamma that minimizes the RHS is not a solution to our ultimate search problem, right? It is just a convenience. Okay. So can we do better using Lipschitz smoothness? That's the right hand side. I already gave you a hint that Lipschitz smoothness will give you some guaranteed decrease. Okay. So what do we see here? You see that Lipschitz smoothness has put some upper boundness on the curvature, upper bound the curvature. So you're saying if this is the function, you had convexity give you some lower bound supporting hyperplane. This is convexity. We use one more, right? So this curve says, you cannot be curved more and more than this dotted curve. Right? Right. So the notion of better, again, I refer you back to the slides I showed, Q linear, R linear, other convergence. What is the notion of better? You need to look at that. But for us, better practically means, can we change this t greater than equal to r square, b square by epsilon square? An ambitious t greater than equal to some proportionality times 1 upon log epsilon. I mean, that's one aspiration. The other one is say, okay, can I make this r square, b square by epsilon? At least better than epsilon square. Epsilon square is totally embarrassing. Okay. Yeah, and then practically speaking, for another decrease by factor of 0.01, a sufficient condition. Actually, I've used this word, we need a sufficient condition. Is that a sufficient? I should write it as sufficient condition. I think I should just write a sufficient condition. A sufficient condition is the need for 10,000 more iterations. I mean, even that as a sufficient condition, we are not happy about. It may be faster than that in practice. So a little bit about Lipschitz smoothness. What does it give us? Some properties help. And if you remember, I had given you one more homework problem last time, composition, right? I told you, can you show that compositions of two Lipschitz smooth functions? And what do you know about the composition of two Lipschitz smooth functions, right? So we had known some properties earlier, that bounded gradients is Lipschitz continuous f, for smoothness is Lipschitz continuity of gradient of f, and the sum of Lipschitz smooth functions is also Lipschitz smooth. A positive linear combinations of Lipschitz smooth functions are Lipschitz smooth. And now I didn't do this earlier, but if you take some, right, if you take some linear combination ax plus b and use gx, then the convex function f of g of x is smooth, is also smooth. So this is a kind of composition, a simple form of composition, right? Composition with some linear transformation. Now the interesting thing is this gives you a Lipschitz constant is, and so the Lipschitz, the reason I give the example is that Lipschitz smoothness constant is not going to be easily determinable in the case of compositions. Okay, if you remember, composition for convexity, subgradients, all that was easy, but Lipschitz smoothness is a little trickier. For example, here the you'll have to look at the lambda max of A transpose A, that is the spectral norm of A, to compute the Lipschitz constant. So basically, it's L times the spectral norm. That will be the new, assuming L is the Lipschitz constant for the function f itself. Clear? Yeah. So now I had left you as a homework, logistic laws. We showed how the logistic laws is Lipschitz smooth, right? And I said, well, it's two composition. But then the natural question is, okay, in practice, how do I compute their Lipschitz smoothness constant? So I'll do that very briefly. I mean, I'll just bring back logistic laws, right? I think it's important to just appreciate how the L might get computed. So, so for the logistic laws, we saw that F basically can write it as F1 of F2 of theta, right? Where F1 is a log of 1 plus e raised to t, and F2 is just a linear function. Yi xi transpose theta or theta transpose xi, either which way, this linear. So this we saw, but I had left it at this, that it would be therefore be Lipschitz smooth. In fact, it is also convex. And we never delved into how its Lipschitz smoothness constant will look like, right? How bad or good it will be. So can you guess anything? I mean, I talked about spectral norm, right? If f of g of x, f has Lipschitz smoothness L, g is ax plus b, then it will depend on the spectral norm of L times the spectral norm of A. So what do you think will happen here? Isn't there a similar nature? Isn't the function inside a linear transformation? Right? So you would again here have some spectral norm. Spectral norm of what? Yes. I mean, this F2. So what is the connection between, since we're anyways talking about smoothness, what's the connection between theta transpose xi? Okay, basically there's a yi also there. And minus yi. You can view this also as minus a yi xi transpose theta. Right? So this either which ways. I mean, theta is the theta is argument. Oh, I just put theta at the end, that's also fine. This is a one-dimensional A, right? So what would it lambda max be? What would the consideration of lambda max be on a scalar? You understand the question? How do I compute the Lipschitz smoothness of xi transpose, right? Okay, so I mean the sketch is basically as follows. As I said, this is by chain rule. On the left hand side is as application of chain rule, gradient of f1, f2 theta. Now what you can do is basically the trick here is f2 minus yi theta xi transpose, that minus yi xi you take it to be pi, some vector pi, and so that pi important thing is somehow represent, yeah, uh, f1 also in terms of the pi, and that is the key here. Okay, so this will give you basically pi. This what I was referring to as xi is basically pi. So on here for the you'll have to invoke Cauchy-Schwarz inequality. I don't want to spend too much time on this, but you can basically invoke Cauchy-Schwarz inequality and show that you'll have a term involving the other dot product. Okay. And in general, you can show that this leads to the Lipschitz smoothness to be proportional to the max value of the PI transpose. Okay, so let's go to the main thing. That was just to give you a flavor of how you can derive Lipschitz constants, Lipschitz smoothness constants. Okay, now the whole thing is going to be your interaction. You'll have to look at our magic box here. You'll have to pick a trick from here. So consider this Lipschitz smoothness. I started with Lipschitz smoothness. So actually, what I'll do is I'll first talk about guaranteed decrease, and then we'll do the convergence. Okay. So if you have y f of x, y plus f less than equal to f of x plus blah blah blah, this is Lipschitz smoothness. If I just replace y by xt plus 1 and x by xt, what do you get? I just did a simple replacement in Lipschitz smoothness. Y by xt plus 1 and x by xt. What do you get? Sorry, yes. It's not just less than f of xt, it's less than f of xt plus. So minus gamma gt minus or rather plus gamma square right. What can you do next? You understand what I've done? L by 2, sorry, L by 2 is also. That's how can I get a guaranteed decrease here? So this is the red part we have read on the board. The left hand side, is it independent of gamma? And the right hand side depends on gamma. What will you do? And then what happens when you minimize the right hand side with respect to gamma? This for all gamma. So basically saying for all gamma, yeah. So minimize, if you minimize upper bound with respect to parameters, I've just given the list of tricks. So obviously you don't get into telescopic summing. So if you set the RHS, you'll get basically you should get gamma is 1 by L, right? This holds in the worst case. Gamma is 1 by L. So if you what is the value then? If you substitute gamma as 1 by L here, what do you get? minus L square by, well, 1 upon 2L. 1 upon 2L. One upon 2L norm GT square. So this 1 upon 2L norm GT square, right? That is a sufficient decrease. Right? 1 upon 2L norm GT square. This is a sufficient decrease. Obviously, if as GT tends to 0, the guarantee of sufficient decrease also decreases. But this is exactly where L matters. Now, why I bring this up also is when we take the example of this lambda max. So if you take a matrix which, right, which has large ratio of major axis to minor axis, right? Then what will happen? I mean, basically spectral norm. What will happen to the spectral norm? I'm saying, what is the effect of changing nature of your A matrix? A matrix, how does it affect the spectral norm? A transpose A, lambda max, yeah. So for a fixed area, if you have more skew, the spectral norm will increase, right? More skew, basically, it's an. So if you have too much skew, I mean, too wobbly a function, then you have 1 upon 2L. The guaranteed decrease will also shrink. I mean, what is smoothness saying? It's you're well behaved. You're not too wobbly. You're not too curved. Too curved means too wobbly, right? So just to draw the connection here, a wobbly function implies less decrease. Less decrease guaranteed. You see why smoothness is being. This is we're not even got to. Well, did we use convexity? Did we use convexity? We did not even use convexity, by the way. You see, smoothness has played a role even without convexity. Okay. Yeah, so no convexity so far. So let me write this. Then the connection between spectral norm and L smooth and L. Okay. Is clear, everyone? Okay. What else? Now what can we do next? We got some guaranteed degrees, fine. That was a side discovery in some sense. We've not even used convexity. We've not got to 1 upon epsilon or log of 1 upon epsilon. We need to get there. So what do we do next? Telescopic summing? So early? Fxt plus 1 f less than equal to fx. You can keep doing this and you'll say, well, G not G zero norm square, right? Good try, but maybe a little too early. Huh? Convexity, right? But the thing is, you'll have to get a very good point. See, the thing is, you're dealing with norms here. Moment you have to deal with norms or quadratic expressions, basically. What connects quadratic expressions to convexity? No. This entire analysis is without strong convexity. It's only Lipschitz smoothness. What did we do last time? So the parts on the right hand side will help you connect the dots. Which two properties? Okay, please look at this carefully. The two properties here, in convexity is of course one. But which is the other property which will give you some quadratic expression? Moment you see a quadratic expression and you have to match that with some other quadratic expression, which property will you use along with convexity? Just look at the board here. Which property has quadratic? First one, right? I mean, L continuity had, but now we have L smoothness. So you use this and this algebraic trick, right? What we did last time. That is just a repetition. Okay, so just highlight reason without convexity. Assumption Lipschitz smoothness gives some guaranteed decrease in every iteration. Now with that, yeah, we have nice property gradient descent is guaranteed to decrease the function value for a Lipschitz smooth function. Okay, so and now, yeah, just a small comparison before we move to the next analysis. If you remember in Lipschitz continuity, the gamma was RB by square root T. Whereas here, gamma, I mean the existential gamma, so the worst case gamma itself is 1 upon L. These are like values of gamma yielding tightest upper bound. So just interesting contrast, right? And in practice, gamma being inversely proportional to 1 upon L is actually good. Because the more curved upper bound, let's say L is large. That means a large upper bound on your curvature. Then you should take small steps. There's some intuition building up here. There was not so well intuition. There was basically in terms of, the Lipschitz. Well, we had a 1 upon V instead of 1 upon L. So that parallel is there. B is basically from Lipschitz continuity. But you can't just use 1 upon B there. You have to balance it with the original distance. See, Lipschitz continuity is about rate of change of the function. And rate of the change of function will depend on how far the first iterate is from the last iterate, the final sort of iterate, f of x, not minus f of x star. Right? So that's why R is coming up there. You have to normalize the B against the R. And also you have to look at the iterate numbers. The square root T comes because of that. Okay, just some rationalization. So it's good to also make sense of what is coming out, right? Not just use them. Okay. So yeah, this f of xt is less than equal to f of x t. So you could just do the following, right? Somebody was saying, I will just sum up. You can do telescopic summing. If you do telescopic summing, what happens? You'll get that the summation of gt square is less than equal to f of xt minus f of xt plus 1 sum. Right? Is that helpful? Because that was the suggestion that came up. Let's see what happens, right? If you apply telescopic summing, so you will get the norm of gt squares is less than equal to f of x naught minus f of xt. So we have used telescopic summing as a first, but let's write this down. Oh no, okay, maybe you can register it. We have applied telescopic summing and upper bounded the sum of the gradient norms with f of x naught minus f of xt. So that's there. But what was the next step? After you do telescopic summing, right? Yeah, this basically is because you have got f of x1, minus f of x1, f of x2 minus f of x2 cancelled out. Then we are coming to the next question. So the sequence has changed a bit here. What did we do? The first thing we did was we applied strong convexity. And then our order change, apply telescopic summing. And then can we apply convexity assumption now? So can this become our second, followed by algebraic trick, third steps, right? I'm just changing the order of these steps. That's it. Yeah. So that's the second analysis. By first part of the analysis is done. And it's exactly what we did earlier. In the previous analysis, we first brought in convexity and then used Lipschitz continuity. But now we brought in Lipschitz smoothness first and then brought in convexity along with the quadratic inequality. And the other intuition, like the other drive, so far, there is no X star. See, that's the other question you should have. I mean, how long will you keep dealing with X naught, XT, XT plus 1? You have to somehow start measuring things from X star, right? So convexity is what will give you a calibration with respect to X star. Why? Because you'll say, what do you say? F of X star. Yes. What's the inequality you'll use? Not strong convexity, just convexity. Less than equal to. Right? So you'll use this and then you start using the whatever x1, x2 in the quadratic expression to be the something corresponding to xt here, right? Okay. So this is the analysis to simple expansion. You remember this, right? It's exactly reproducing what we did earlier. I won't spend more time. GT. So basically, you've done two things. I mean, you can use them in different orders. Here, what I've done is I've used the quadratic expansion first and then bringing convexity. It doesn't really matter. Because what you're doing here is after you bring in the convexity, you'll try to bring or rather upper bound, lower bound the dot product through through a quadratic expansion. Right. So this dot product which you see there, GT transpose XT minus X star, is what is being expanded here. Right. Now you can do a telescopic summing there. That's what we did earlier. Right. But do we need to do telescopic summing? Here is the question. We may not want to do all this again. See, earlier what we did, I'm just trying to draw, recalling, right? Drawing a parallel. Earlier we applied the quadratic expression and then we did telescopic summing. We summed this over t iterations. But do we need to? We have already done telescopic summing differently, right? I'm just recalling what we did. Sorry. Okay. So it doesn't, by the way, it doesn't hurt to do it. I mean, you can do telescopic summing here. The thing is, you have to start getting relationship between terms here and the terms you got from the telescopic summing on the L. So what we do here is basically invoke convexity. Exactly like we did for Lipschitz continuity. We invoke convexity, bring in the quadratic expansion. Yeah, I think the rest is just exactly the same as what we did earlier. So I won't spend time again. The difference now what the difference will turn out to be is that this is very interesting. the summation of xt minus f of x star less than equal to gamma by 2 norm gt square plus 1 upon 2 gamma norm x1 minus x star square. So earlier, the inequality we had for Lipschitz continuity plus convexity, you had this, your minimizer was 1 upon r upon b square root 2. Right? This is the gamma. Here, when you try and minimize the right-hand side, it will turn out to be gamma by L again. Remember, gamma by L is what gave us the, the minimizer for the right-hand side, which gave us a guaranteed decrease for Lipschitz smoothness. The same gamma by L is what will also minimize the upper bound here, which is very good to hear, very, very good to know. So, the gamma by L is not a random number that we got then. That gamma by L is very consistent with the one that also minimizes the upper bound here. Okay. Okay, so we set this to 1 upon L, and then now we have got a simplified expression. F of xt plus f of x star summation is less than equal to f of x naught minus f of xt plus L by 2 x naught minus x star square. Okay, I'm just going to draw the highlights here rather than go through the entire proof, which you can do anyways, go over anyways. So what we do next is, we have to also bring back our strong Lipschitz smoothness, right? So this 1 upon 2L norm gt square by virtue of the minimization of the right hand side is less than equal to f of x naught minus f of xt. That's what we are showing here. And 3 was basically this expression. 3 was the expression, right, which we got by using Lipschitz smoothness. So 3 is our Lipschitz smoothness equation. So f of x naught minus f of xt we got there as lower bounded by norm of gt square summation t is equal to 0 to t minus 1 divided by 1 upon 2 by L. Now, right, so this same, now you've got a similar kind of expression here, norm gt square by virtue of convexity. We've got a similar, and all the other tricks, we've got a similar expression here. And so therefore, this becomes your connecting point between the summation of f x t minus f of x star L by 2 x naught minus x star square and f of x naught minus f of x t, which we got from strong convexity. So that's why you get the yellow part. Yellow part is a strong convexity part. Sorry? This one? Yeah. Okay. Thanks. There was a small time. Yeah, thanks. So this will be x naught. Now, what does this tell you? X naught minus x star immediately reminds you to invoke step 4, right? Question is, can we do away with this ever? Right? Is there a way we can avoid working on x naught minus x star?
Said that Rana took 1 mile go to work here. How did we?
Oh yeah, thanks for pointing this out. So this holds for any L. Okay, this was not by minimization. I'm sorry. This holds because we used the L that minimizes earlier. We just use the same L. This holds for any L because the left hand side is independent of L. So it holds for the minimizer, it also holds for any other. Good point. Yeah, I know in the slide I've written minimize. I think I said that that was a slip. Right. So in fact, I've said an additional note is that gamma is 1 by L is good enough to maintain that same upper bound. Okay. The right hand side did not have any, the left hand side did not have any gamma. So I was free to choose a gamma, but you can show in retrospect that this maintains the upper bound. And this was inspired by sufficient decrease. Okay. So now what can we do? I mean, we need to finish the convergence, right? So how do you go from here to convergence and speed of convergence? Our upper bound and function value, what are the number of iterations, and so on. How do you do that? So we had the following, right? I mean, take the terms in yellow to the left hand side. Right, so that gave you f of x t minus f of x star summation. So I've basically got one more. It was t0, t equals 0 to t minus 1. I've got t. So you see the change. T equals 0 to t minus 1. By bringing these two entities on the left hand side, we are cancelled out f of x naught. And we have introduced a x capital T on the left hand side. Right. And you can show that, if f of x t, so since we have sufficient decrease, at every iteration there is decrease. So you can show that f of x capital T is less than equal to f of x small t for any t. Right? This is earlier we had to use an x hat. So that's the other difference because of the sufficient decrease. Now, so on the left hand side earlier, the analysis was in terms of f of x hat, where x hat was the kind of minimizer so far. More bookkeeping to be done. On the right hand side, it's just in terms of xt. Okay, as a subscript t. Subscripting. Okay, so now all this implies that f of xt minus f of x star, right? If you take the left hand side, the minimum value of the left hand side, just with respect to t, then you get xt, and right, you just divided both sides by t. Divide this entire thing by t, you get L by 2t, and if you divide this whole thing by t, then that is greater than equal to t times f of xt minus x star divided by t. So how do you go forward? Well, you already hinted what we could do here. F of xt minus f of x star is less than equal to L by 2t times. What do we do to x naught minus x star square? R square. L r square by 2t. Okay. L r square by 2t. How does it compare with the earlier one? Let's write that down. Earlier we had, I'm going to erase this part. L r square So if L r square by 2t should be less than or equal to epsilon, then that's a sufficient condition for f of x t minus f of x star is absolute value less than or equal to epsilon. I've just drawn parallel, right? I'll again talk about sufficient condition here. Is this clear? This I'm just drawing. I'm just drawing a parallel here. So what will that mean? What should t be? Right. That means t be greater than or equal to, well, basically L r square by. So this, is it better? Let's see. So putting all this together, we have yeah. To ensure that f of x t minus f of x star is less than or equal to epsilon, we require L r square by 2t is less than or equal to epsilon, t greater than or equal to r square L by 2 epsilon. Now, is this, how much better is this? Okay, so to achieve error of 0.01, we require, well, I've used 50, but take it to be 100, that's also okay. I've just taken by 2. Right? So even if we take this to be 100 r square L instead of, I mean, ignore the 2 here, it's 100 instead of earlier it used to be 10,000. So that is a big speed up. Right? So the gradient descent step with step size gamma by 1 upon L seems to be a little there in the assumption, okay? Because it gives sufficient decrease. But you can show that even without that, with RMO conditions, this is very complicated proof. I've taken the simplest path of proof. In fact, my earlier offering of convex optimization, I would do really the worst case proofs. You consider RMO conditions. See, some condition is required. You can't say for any gamma it will work. It won't work for any gamma. You have to say that there's sufficient decrease. It's not right. So under certain conditions on gamma, you can still show that the same convergence is there. Okay. So this is not the only proof. I mean, this is the simpler looking proof. The more complex ones.
Still a load on. Is there like load on T?
We are coming to that. In fact, the upper bound is going to give you impetus. We will come to that. There have been papers that showed that. And how will you show? Okay, there's a question for you. What is the way you would show an upper bound? That, you know, you
You need a load on.
right. So think about it. But yes, we'll talk about it. Okay. As I said, recall this value was only to give a lowest upper bound. In practice, line array search are used, and convergence can be proved with strong Wolf conditions on step size. Okay. So there are some RMO condition, Wolf conditions. I gave example of sufficient decrease. Those are required to do the more rigorous proofs. Okay. Now we'll move to strongly convex functions. Yeah. Sorry. We did. We minimize here. When we were trying to show sufficient decrease, f of x t plus 1 less than or equal to f of x t minus gamma g t plus L by 2, remove gamma square, the smoothness. So we said if you minimize the right hand side with respect to gamma, we know the sufficient decrease. There we minimize with respect to gamma. But I'm saying that is just a one instance of gamma. It holds for many other gammas. When it holds for gammas that satisfy the strong Wolf conditions. Okay. Since you are like really curious, let me just show you what the strong Wolf conditions are. Okay, by the way, if you have stronger convexity, you can the strong Wolf conditions. Yeah, these are the strong full Wolf conditions. Okay, so What is strong wolf condition? I mean, I'm not going to give rationalization. That's in this extra slides, optional slides. So let's say you have two constants C1 and C2. Then the first condition says that the gradient at the current iterate plus the step size T double prime, right, times the step direction delta, which is the gradient here, negative gradient, is greater than some C2 times, okay, some C2. It should be greater than the dot product of the gradient with the step size, with the step, right? C2 times the gradient of the dot product of the gradient with the step direction should be lower bounding, or not lower bounding, it should be less than um, the dot product of the. So basically, what we are saying. Okay, so I think this is there somewhere. Yeah. So basically, okay. So think of the gradient dot product with respect to the step here after you reach, and the gradient dot product after you reach here with the step here. Okay. So this is a step, right? The gradient dot product here and the gradient dot product here. You're comparing the two. That's what's happening here. And your point is, after I do the descent with that step size, T double prime, I am C2 times greater than the earlier dot product or earlier directional derivative. Dot product is directional derivative. Okay. So you get the point. It's making some, the directional derivative has increased by at least C2 times. The second condition, now there are two conditions are operating in tandem. On the first, sorry, that was the second condition. The first condition is that the function value. The second condition was with C2, which was with respect to the gradient dot product, which is the directional derivative. The first is what I told earlier, that the function, there's a sufficient decrease. So you're decreasing sufficiently. Directional derivative is also increasing. So did you understand? This was the first condition, where we said f of xt plus delta t times delta k is sufficiently less than equal to f of xk. So strong wolf conditions, I'll just write that down. And I'll close it by highlighting with respect to the figure here. Sorry. Here. Okay. So strong wolf conditions are and I'm not going to write the expressions again. Just the intuition. Sufficient decrease. And that is in terms of C1. Okay. The C1 is the constant associated, okay, not in this figure, but the expressions I wrote later on. And C2 is sufficient. Earlier was decrease of f, sufficient increase of directional derivative with gamma. That is what C2 gives you. Oh, sorry, I'm sorry. Sufficient upper bounding. This upper bounding. This correct. This upper bounding. See what is upper bounding? So this is upper bounding. What is upper bounding doing? It's saying that you don't go into very wobbly territory. So make sufficient decrease, but don't get into very wobbly territories. right? Because if you make such a sufficient, you make a decrease in such a way that there's too much oscillation, then you'll have a problem with respect to the direction itself. So you want a direction, you want the gamma to lead to a point where the direction can be further trusted. Okay, so yeah, I think the slides have it, but I can. So I just put this slide here. This slide 27 page 32. Oh, sorry, this is it's too small, right? Okay. Can you see this? Is it visible? I don't know why it's starting. Is okay? Yeah. The same 2 points updated here. Okay. So now with this, I'm going to. Was this helpful? You got an idea? Okay. This one. Ah, I mean, this is the same thing which I've written on the board here. No difference. Yeah. Yeah, before this, yes. Yeah. So here, after what we did was minimize the upper bound. Minimize the upper bound of f of xt plus 1 with respect to gamma. Yeah. So there also, okay. So this holds for this holds for any gamma. So it holds for the worst case gamma. Likewise, the other place, here, this right hand side, right, the blue. Now the right hand side is a function of gamma, and left hand side is independent of gamma. So this inequality holds for all values of gamma. It doesn't. It's not that I have to minimize the right hand side with respect to gamma. Yeah, it might give you a different expression. It won't give you L for sure. It won't give you L. It won't give you 1 upon L. It won't give you 1 upon L. I made a mistake earlier saying that it won't. No, I mean, see, it's just that why do we minimize? I mean, minimization is to often get an expression which is kind of. So there are two things. If the subsequent steps involve gamma or any of the other steps involve gamma, you have to be consistent. So minimization is a safety gate check, right? Saying that even in the worst case, with this gamma, it should hold. But in this case, there is no subsequent step. We've already taken care of the minimizer with respect to gamma in the first step. So there's no problem, right? As I said, now there has to be consistency across these steps. You have one inequality in terms of gamma, this one, and there's another inequality in terms of gamma, this one. Now you need a gamma which satisfies both. Now what's interesting is this involves the norm of the gradient square, right? And that also involves the norm of the gradient square. The difference is this involves a function difference fxt plus 1 minus fxt. That involves a difference of x1 and x star, right? Some of the difference of points. You can show that this relationship between the two expressions involving gamma is very similar to what the strong Wolf condition talks about. One inequality is in terms of the first order conditions, which is upper bounding increase of directional derivative. The other is in terms of the function fxl. So you need these to be in sync with each other. That's the key. Like the strong Wolf condition talk about one way of syncing up. Is this clear? No. You'll end up getting similar. It's possible that some of the factors change, but the 1 upon epsilon would become 1 upon square root epsilon for sure. That would happen. I think the order which we talk about won't change. I'm going to just conclude the next 1 minute. What I want to do is bring up strong convexity and leave it for your thought process, right? I don't want to keep doing strong convexity also in the same great details. Question to you is, again, we have this magic box of different techniques. What all will be useful here? So I've said smooth plus strongly convex. Now this is our really solid combination, where we have a upper bound as well as lower bound on curvature, right? So what is your bet? What would you go with, right? So let's say, again, I want to just give you a characterization. You have a lambda max, a lambda min, right? The max curvature and min curvature, and the function is somewhere in between. Lambda max is like the L, and lambda min is like the mu. And there's a connection between L and mu. What is the connection? L is greater than equal to lambda max, or L is certainly greater than equal to mu. That you agree, right? We had the two inequalities for convexity and strong convexity and Lipschitz smoothness, and they were exactly contradicting each other. One was an upper bound on the curvature quadratic curve that upper bounded the function's curvature, and the other was in terms of L, and the lower bound was in terms of mu. So L has to be greater than equal to mu. Remember this. L has to be greater than equal to mu. And this itself is giving a hint. Can I get to log of 1 upon epsilon by using this mu by L somewhere? That's the key. This L by mu, or sorry, mu by L. I know it's less than 1, and therefore it should just sometime vanish. If I can exponentiate and like 1 upon mu by L, 1 minus 1 upon 1 minus mu by L raised to something large number, or 1 minus mu by L raised to some large number itself, I would expect that term to vanish. And that can give me 1 upon log of 1 upon epsilon kind of guarantee, right? So think about this. You can start with the previous analysis, the dot product of gradients, right? So you could have started with this dot product of gradients. The deviation is, instead of convexity followed by telescopic summing, why not strong convexity next? So why not bring strong convexity a little earlier, right? So that's a homework problem for you to think. And the rest, I'm going to leave it to you for homework. Plus, so please give some thought. I think you have many of the elements of the recipe with you. How do you use strong convexity hereafter to get better guarantees? And I'll give you the hint already. As I said, we are hitting log of 1 upon epsilon. What does that mean? T is greater than equal to log of 1 upon. right? Which will mean that you're just going by similar thing, right? That means epsilon should be, or what should happen? What do you expect? If t is greater than log of 1 by epsilon, what's the inequality you expect here? Yes. Some e raised to t, some factor raised to t. Can it be a factor? So my question is, can this be a function involving u by n raised to t? So this is where we are targeting to get. Okay. Okay, I think that's my homework problem for you. Thanks. We'll end here. So on Friday we'll do, on Thursday we'll do some recap, complete this proof for sure. This is interesting, very interesting. Almost a homework problem. Come back with any doubts also on Thursday. Because I will not do, other than this, we'll not do too much new. We'll keep it for doubts as well. And we have TAs also come here on Thursday. See you on Thursday then.